SVD algorithm. I mentioned the singular value decomposition before. Okay. Where you're decomposing A is U times sigma times V transpose. U and V are orthogonal. A is an M by N matrix, it's no longer square. And sigma is a diagonal matrix containing the singular values. Okay. Now, I mentioned some properties of the SVD quite some time ago. So one of these properties that is useful now for actually computing the SVD is, okay, it's notation. If I let V and use a column partition, then it turns out using the singular value decompositions of A and A transpose, both, which is, I can just take the transpose of this, I get A transpose A times each column of V, the right singular vectors. Need more notation here. So we have a singular value, sigma 1, sigma 2, and so forth along the diagonal, is equal to sigma j squared Vj. So this shows a relationship between the singular value decomposition and the symmetric eigenvalue problem. That the columns of V are eigenvectors of A transpose A, a symmetric matrix, and the eigenvalues are just singular values squared. Similarly, I have this breakdown for U. I have A transpose Uj is equal to sigma j squared Uj. So if you use columns of U are eigenvectors of A transpose, and again the eigenvalues are singular values squared. So you might think, oh, okay, I don't really have to do anything special for the SVD. I can just fall back on one of these symmetric eigenvalue problems. So a simple-minded algorithm is you can go ahead and compute A transpose A, and I'll call that B. And then use the symmetric QR algorithm, and you get, so that basically computes the sure decomposition of B, and you get V sigma squared V transpose, and then you use this relationship between U and V. If I multiply both sides of the SVD by V, I get A times V is equal to U times sigma. So I can use that relationship to get the columns of U. And then I'm done. I have the SVD. So you might think, well, there isn't really anything to talk about, but yes, there is. You don't do that. Bless you. It's almost as bad as computing the inverse explicitly. Because anytime you carry out an operation like this, you get a loss of information about the entries of A due to a round-off error in computing the entries of A transpose A. So if you have an algorithm that calls for computing A transpose A, you want to find a way to work around that. Don't compute this explicitly, but try to do it implicitly by coming up with an algorithm that works on just A. So we still have this as a starting point at least. We're just going to try, so just like I did with the Francis QR step, we're going to try to fake all of this. Now watch this gradually algebra people, we're such cheaters. I think it's why, like, I'm learning or teaching about their work because of how sneaky they are. Okay. So a practical SVD algorithm. That's due to my advisor, Gollum, and Bill Kahan, who's a retired professor at UC Berkeley. Okay. So what you do is, it's similar to what you do in the eigenvalue problem, where you're using household reflections to reduce A to Hessenberg form. But now what you do is, so you're using household reflections on the left and on the right. So both these matrices, V1 and U1, are accumulations of householder reflections to get a matrix B that's not the same B as I have over there. It is an upper bidiagonal matrix. So we have diagonal entries, D1, D2, up to Dn, and then super diagonal entries, which are the F's. Everything else is 0. Okay. Now, the nice thing is, we can do this because we are not trying to preserve eigenvalues here. This does not have to be a similarity transformation. We just want to wipe entries out. So, since these household reflections in V1 and U1 are different, I can go ahead and basically upper triangularize A coming from the left, and then I'm wiping out entries above the superdiagonal on the right using the transformations in U1. Now, as a result of this, if I were to compute B transpose B, that would be tridiagonal. So that's what happens when you multiply a upper bidiagonal matrix of its transpose. But we're not going to do that. Instead, we're going to just work on B directly. And so this is just a side note here. Because what we could do is, we could apply the symmetric Cure algorithm to this tridiagonal matrix we just got. But again, we would get that same loss of information. So we're not actually computing that. Okay. So here's what we do instead. We're going to use an iterative process, much like the QR algorithm. And here's what we do in each iteration until B is reduced to diagonal form, which would just be our sigma. Okay. All right. So what we do is, it's similar to what I showed you earlier today. I'm going to compute a given rotation and G1 will be the first given rotation, so I should make that explicit. The first given rotation that would be applied to T minus mu times the identity, where mu is the Wilkinson shift. Because this is a still symmetric eigenvalue problem, that's the shift we're going to use. Now, for this matrix, like I said, we're not actually computing T. All we really need to do, though, is we only compute the first column. Right. Oh, actually, the first column, well, to figure out the rotation, we also need the Wilkinson shift. So we need the lower right 2 by 2 block for purpose of computing a shift. Or you can use whatever shift you want. But again, we want the most rapid convergence, so Wilkinson shift is the most practical idea. So we only have to compute a small portion of T. First column, lower 2 by 2 block, and we'll get enough information to figure out what G1 is supposed to be. All right. So then what we do is we apply that Gibbons rotation on the right. Now, what we're faking here is applying this Gibbons rotation to T on the right and left. So applying it only on the right of B, because you see what happens. This is BG1, this is BG1 transpose. So we've accomplished that first similarity transformation without actually performing it. Okay, now B is upper bidiagonal. What happens when we apply this Gibbons rotation?